Right. As I've already been announced, I'm going to talk a little bit about the work I've been doing with some colleagues and with students on dark matter searches in the radio frequency domain. And this is going to be primarily about MeerKAT and a little bit of sort of future look towards the SKA. So the talk outline is quite simple. I'm going to talk a little bit about why dark matter matters. I'm going to talk a bit about how we go about searching for something like dark matter, which on the face of it doesn't directly emit any electromagnetic signals itself. I'm going to differentiate here between two kinds of dark matter, WIMPs and Axions, both of which we can search for using the MeerKAT instrument. I'm going to do a little overview of previous searches with radio telescopes and a little bit of gamma ray stuff in there too. And I'm going to talk about MeerKAT itself and the cluster legacy survey, which is the data we've been using for a lot of this work, show off some results, and then summarize everything at the end. So the first topic is why believe in dark matter at all. So there are quite a few points of evidence, and as we'll see, they can be quite difficult to explain all at once, but by doing something like modifying our theory of gravity. So the first kind of observational evidence is the fact that stars move too fast to be gravitationally bound by the visible matter in a galaxy. So we'd have the standard old example rotation curve that people always use with the observed rotation curve in whatever this color is. Sorry, I'm colorblind. The expected curve, which I think is in blue. And the expected curve would be just the velocities of these stars as a function of radius, if you were just using the visible matter distribution in the galaxy. So of course we see the observed case, and once we supplement this with this dark matter curve here in the dotted line, we can match the observations. So that gives us the first reason to think that dark matter is something real. Of course, this could be explained by modifying gravity, this particular piece of evidence. The next one that is quite difficult to explain with modified gravity is the cosmic microwave background power spectrum. So in this case, we're talking about correlations between the little anisotropes in the CMB, and each of these peaks tells us something about the oscillations in the primordial plasma just before the CMB was released. Now, the particular pattern of peaks we have here, where the second and third are of similar height, tells us that something is going on with the matter that is expanding and contracting during these oscillations, and that we require some component of matter that does not feel the pressure produced by photons. So this is evidence coming from an extremely different scale to the galaxy evidence we looked at earlier, and this is much harder to do with simple gravity modifications. And then of course there's the bullet cluster, which is a nice example of gravitational lensing evidence for dark matter. So the blue marks out the area of high gravitational lensing, and the pink marks out the X-ray emissions. So the X-ray emissions in a cluster like this will be tracing the baryonic matter, and the blue tells us where most of the mass is. So we can see that this object here, which is a collision between two galaxy clusters, looks like something where we've got two dark matter halos that have just passed through each other, because dark matter is essentially collisionless, and have left most of the material lagging behind in the middle because it does experience friction during this collision. So again, this is very hard to do with modified gravities. We've got this variety of evidence on different scales, and it's really hard to account for all of this without something like a particle or particle dark matter. So we have an abundance of evidence that says that dark matter matters. And what we really need to do then is work out or summarize what we know about it, so we can see what we need to find out. So what we know about dark matter is, of course, this standard universe content diagram, where we see dark matter makes up about 27% of the energy budget of our universe, and so substantially more than the visible matter does. So it's important. It's obviously got a mass because it has to account for all these various gravitational effects are what lead us to add it into our models. So it's probably a particle, just in order to comply with all of the evidence. And it's got to be electrically neutral because we hadn't seen it. So that's not a terribly good amount of information to go on, but we can add something in to make this a bit easier. So there are three processes people usually consider when searching for dark matter. So there is scattering, where dark matter bounces off standard model particles, which people usually do in large underground experiments with giant tanks of xenon. There's actual production where dark matter particles will be produced in the LHC. And there's, of course, annihilation or decay, where the dark matter particle itself or self-annihilates or decays or annihilates as an antiparticle, depending on its own properties, to produce standard model particles. So these add in potential connections to the standard model, because without any additional connection to the standard model, it's unlikely we'd ever be able to learn any, or at least not very much, about dark matter beyond that it has a mass and that we apparently need it. So the case we're focusing on here is, of course, the annihilation route. So we're going to look at areas in the cosmos which have which are purported to have very large densities of dark matter, and we'll look for the signatures that occur when our dark matter particles annihilate each other. So of course, the most generic case we can look at is WIMPs, so the weakly interacting massive particles. They're very generic, so lots of potential models can be put under the WIMP banner. So it's also useful to look at them because we can constrain so many different models all at the same time. So the WIMP is massive, it's neutral, it has weak interactions with both itself and with the rest of the standard model. And of course, we'll assume it can decay or annihilate, right? And the annihilations which I've pictured here, there are two cases where we might be interested in, and the cases are when the annihilation produces electrons and positrons, or when it produces photons. So note this won't be a direct production of photons, because as I mentioned, this particle is neutral. So it will have to, it produces something else that's censored underneath this gray blob, okay, because some horrible, complicated QFT processes go on underneath here. And the final result of those horrible processes are the stable particles we see on the right-hand side. So the horrible processes that go on in here we call the annihilation channel, and we usually just we label our annihilation channel with the first thing that comes out of the dark matter annihilation. So for instance, if the dark matter annihilates into B quarks, we'll have a B quark annihilation channel. And it'll usually be quite heavy standard model things that people consider as the immediate annihilation products, which is a kind of a hangover from supersymmetry. But we can, as I mentioned, use a lot of different models as well. So what we're actually looking for when it comes to studying dark matter in this way that people tend to call indirect, when we're looking for the consequences of annihilation or decay. So we have dark matter particles annihilating in some distant cosmic structure. This can produce photons. Now the photons that will be produced by this directly, so that just come out of the dark matter or come out of the decay process itself. These will be very high energy, because dark matter is usually quite massive. For unitarity reasons, WIMPs usually need to be quite above about a GeV or so. And so this could be observed to things like the Fermi gamma ray satellite. If you go up to heavy enough WIMPs, these gamma rays can get extremely energetic, and you might need something like HESS or the future CTA. In the other case, where we produce electrons from the annihilation, these electrons are being produced inside a cosmic structure. And these kind of cosmic structures will be pervaded by magnetic fields. And high energy electron plus magnetic field equals synchrotron radiation. And this can, of course, be observed with MeerKAT. So that's where the theme of this talk comes in. Now, this isn't the only dark matter model we can observe with, or type of dark matter we can observe with MeerKAT, because we can ask the question, what about low mass dark matter? Well, one popular candidate for low mass dark matter is the Axion, which is usually considered to have masses below an electron volt. What is an Axion? Well, an Axion is quite a strange particle. It's introduced to account for the fact that neutrons have no electric dipole moment. Now that sounds like a bizarre thing to try and fix, because neutrons are neutral. Obviously, they have no electric dipole moment. Well, it turns out that the vacuum effects in QCD are quite complicated. And in fact, there is a single parameter which you can't predict a value for from first principles, from the Lagrangian, etc., of the standard model, that if this parameter is not zero, the neutron, despite being neutral, would have an electric dipole moment. So we can't predict theta, and people often describe it having to be zero as sort of unnatural. Maybe your mileage on this argument might vary, but in order to satisfy the particle physicists who didn't like this, someone came up with the idea, well, Pecci and Quinn particularly, came up with the idea that if you replace theta, this parameter, with an actual field in quantum field theory, so adding a new particle, essentially, you can naturally make theta very small, because this theta is going to be the vacuum expectation value of the particle, i.e., essentially the number of particles so the value of the field on average in the vacuum. And of course, if it's a field or a particle that you won't commonly produce, then it'll have a very low vacuum expectation value. And this particle gets called an axion, and it's extremely weird. The first weird part is named after a detergent. Okay, that's where the name Axion comes from. Apparently because it was meant to clean up problems in the standard model. So, as I said, axions are weird. In the presence of a magnetic field, an axion can turn into a photon, and vice versa. Photons can turn into axions. Very strange, right? They can, of course, do boring old decay as well, where the axion turns into two photons. This is extremely slow, however. So the sort of orders of magnitude longer than the lifetime of the universe slow. So notably the photons in this case are at frequencies given by the energy of the axion, in this case 2, but it's also combined with the strength of the magnetic field. So what you're looking for if you want to go hunting for axions, if you look for magnetic conversion, you could be looking for missing photons. So photons that have been turned into axions and thus don't arrive in your telescope, or aren't detected by your telescope, maybe I should say. We could get new photons that are spontaneously generated by axions. We, of course, need quite a strong magnetic field to see this. So neutron stars are often used. And in previous work, myself and my former PhD student, Ahmed Ayad, who's in the channel, actually looked at the jets of AGN previously as well. So plain old decay is, this produces a spectrum, by the way, I should note. A plain old decay produces a continuum spectrum. Plain old decay is narrow line emission. So it's very focused around the frequency set by the axion mass, essentially. Frequency around about half the axion mass, not quite half precisely. For relatively small axions, below 10 to the -4 electron volts, this sits in the radio band, so in the range that MeerKAT and SKA can observe. We need to consider stimulated decay in this case. So just like stimulated emission with a laser, with the laser, we use stimulated emission to get a cascade of photons because of photons that are present already in a particular frequency mode, and they make it more likely that excited atoms will follow the transition with the same frequency. In this case, having lots of photons around at the same frequency that the axion would emit photons at, if it decayed, encourages the stimulated decay of the axion. So of course you need a large photon background at the same frequency, but because it's line emission, the background doesn't actually necessarily complicate your observation of the axion itself. So it's the one case in dark matter where we're actually looking for large baryonic backgrounds. So the kind of signature dark matter leaves spatially in a radio observation is diffuse emission. So diffuse emission, an example here in the red on the left, is there's no clear point source, right? You can't actually say where any of this red emission is coming from. It's just a diffuse cloud. And dark matter related emissions would have to look like this because dark matter exists in a loose halo around the visible visible structures in our universe. So we'd expect it to have very strong central emission because the dark matter the halos tend to be quite steeply peaked. They're very large densities at the center and they tail off quite fast on the peripheries. So this is in contrast to point source emission, which is the most common kind of emission you see, which is so the little black dots in this image, on the image on the right, So this is essentially emission that has a definite point of origin. We know it's coming from somewhere. So of course, in radio, we need to get rid of all of this emission first. So we do something called source subtraction, where we characterize all of these little point sources that we aren't interested in, and we subtract them out so that our final image just has diffuse emission that we can hunt for dark matter in. So how do we go about predicting this emission? Well, in the case of WIMPs, we have to solve a diffusion loss equation in order to find the electron distribution psi here. So this diffusion loss equation is in fact quite nasty to solve because it is a partial differential equation and at least second order in space. So it's a nonlinear partial differential equation. It's quite an unpleasant thing to have to attempt to solve. It's essentially characterized by three properties: a diffusion function, which tells us how eagerly the electrons move away from where they appear, so away from the site the dark matter annihilated at. The energy loss function, which tells us how these particles lose energy as they move away. And finally, the source function, which tells us how many electrons are being injected by dark matter. So to solve these equations, we use our own custom written piece of code, which we hope to make public quite soon. It's called Dark Matters. It uses a Crank-Nicolson discretization, and essentially, if you've ever worked with code like Galprop, it uses the same method to solve this diffusion equation. So it ultimately results in us solving large matrix equations, most of which the entries are zero, so we use a very powerful sparse solver to make this fast and accurate. This particular method was worked on by my PhD student, Michael Sarkis. So essentially the ingredients here are particle physics, the dark matter halo information, the magnetic field, the diffusion environment, and this all goes into dark matters and it pops out nice radio predictions for us in the forms of Fitts maps if we want them. So when it comes to predicting axion emissions, the equation looks a lot simpler, because all we have here is a simple equation for essentially the surface brightness, which is given in terms of a line of sight integration over the density of axions, and some additional parameters like the velocity dispersion and the decay or conversion rate. So this will work for both decay and magnetic conversion. So of course, this decay rate can be hard to compute. For magnetic conversion, it requires quite intensive simulations, and for the decay case, we have to compute the effect of stimulated emission. Okay, now I'm not going to go into any of those details today. I'm just going to leave it at that. So the previous searches for WIMPs in particular that I wanted to talk about, of course, they haven't found dark matter, right? So we're still just saying more and more about what dark matter can't be. The process, well, this involves placing limits on the annihilation rate. The annihilation rate is essentially this quantity on the left, also called it's the annihilation cross section. Okay, and we have the WIMP mass on the x-axis, and these lines are upper limits. So any values above the lines are excluded. Okay, they are not viable models. Now, the gold standard in doing this work is getting stuff below the gray dashed line. This is the thermal relic cross-section, the value you require to have dark matter that's produced during the Big Bang and then decays or annihilates to leave the amount we'd expect or we see in the present universe or at the time of the CMB formation, at least. Okay, so if we can push a dark matter model below annihilation rate limits below this line, we've essentially ruled it out as a viable dark matter candidate. Okay. So you can see here there are quite a lot of attempts that do not pass below this line. These attempts are all radio attempts on dwarf galaxies. I've included them just to give some context. This dot dashed line is the Fermi lat limits from dwarf spheroidal galaxies, a recent reanalysis of the Fermi data. Okay, and finally we have the this blue band, which are recent limits from an ASCAP study of so ASCAP is the Australian SKA Pathfinder, an ASCAP study of the Large Magellanic Cloud. So it's a band because they're accounting for the fact that they are both uncertain about the magnetic field and the dark matter halo in the Large Magellanic Cloud. But as you can see, this is by far the best current limits on this annihilation rate. Note this annihilation rate is only if your dark matter turns into B quarks, but I use these ones as illustrative cases. So what we really want to do is see if we can compete using MeerKAT with this ASCAP limit. And of course, we should be able to, because MeerKAT is a more sensitive instrument than ASCAP. ASCAP is built to be a survey instrument, whereas MeerKAT is more suited to these deeper, more sensitive observations. So we can also talk about searches for axions. One of these has already been conducted with MeerKAT, so by a set of authors, including Prof. Ma from UKZN. You can see that in blue here on this diagram. What this diagram is telling us is, again, a set of upper limits. So anything inside the colored regions or above them is excluded. So it's not a viable model. What we're putting a limit on is the coupling between the axion and the photon. Okay, and we've got the axion mass in electron volts on the x-axis. So you can see MeerKAT gets a small amount of coverage. It doesn't do nearly as well as upcoming experiments are projected to, like ADMX, but it does provide cover for this little thin bit of parameter space here that wasn't being covered otherwise. So that's quite nice. So why MeerKAT in particular? Well, MeerKAT has extremely high angular resolution, which is very necessary for us here. Though I said we're interested in diffuse emission, we are not interested in small sources. So in order to ignore them adequately, we need to be able to characterize them. So we need that high resolution to spot all of the small point sources in the data and get rid of them. Yes, so we need to subtract all those point sources to see the diffuse. So we need high sensitivity because the dark matter emissions are going to be faint. I mean, it doesn't couple directly to electromagnetism. There's not going to be serious emissions at all. And it decays or annihilates extremely slowly. So the emissions have to be faint. We like the wide frequency bands. This is especially useful for axion searches because, as we mentioned, the mass of the axion that you're looking for corresponds to the frequency you use to look for it. So more frequencies means more masses that you can actually look at. And the frequency channels are great because for axions, we're looking at line searches. So we need to be able to characterize our lines well, and that means we need lots of frequency channels. So I'm talking today about galaxy clusters in the most part, and people often talk about dwarf galaxies for dark matter hunts. And as you saw in this plot that I showed here for the WIMPs, basically all of these lines came from dwarf galaxy searches. So why am I interested in galaxy clusters? Well, they've got a couple of pros in their favor. So like a dwarf galaxy, they're highly DM dominated. Okay, dwarf galaxies have the advantage of having low baryonic backgrounds. However, galaxy clusters do not have this advantage. They actually have quite strong baryonic backgrounds. So that's maybe a big negative against them. Dwarves have the problem of the fact that we don't know anything about their magnetic field environment. And if you want to calculate synchrotron emission, magnetic field is very important. So there are quite large uncertainties on the properties of dwarves. And these uncertainties are much less severe in the case of galaxy clusters. For some clusters, we even have magnetic field information, and we have information about a large enough sample of these clusters that we can deduce general trends about what the magnetic field should look like. We also know a bit more about the halo, the dark matter halo around a galaxy cluster. They're big, they're easy to study. The dwarves are very small, it's much harder. So the data we're using is the MeerKAT Galaxy Cluster Legacy Survey. It contains 115 galaxy clusters that are observed at L-band, so frequencies around 1 gigahertz to 1.6 gigahertz. They get about 6 to 10 hours of observation on each one. So there's an 8 arc-second resolution, which is very nice for removing the point sources, and about 3 to 5 microjanskis per beam in sensitivities. This probably doesn't mean anything to you if you're not a radio astronomer, but the arc-second resolution and sensitivity are very good, certainly much better than predecessor telescopes. So these will be great advantages. Now, so 62 were observed with diffuse emission, 56 of which were new, which is a nice discovery for the survey. But we want those that do not host diffuse emission. Why? Well, because we want to put severe constraints on dark matter. And what better way to do it than to say, we saw no emission in this galaxy cluster, therefore we can put a strong limit on how fast dark matter decays or annihilates. So we have two caveats, though. We want them at low redshift, because obviously if they're at high redshift, you could easily not see the diffuse emission because it just could be too faint, okay? And we want ones that have some halo information as well. We need to know something about the dark matter halo. And so far we found 3 good targets. We've found A4038, though there have been some issues with the position calibration of this data. So initially, the data, this mini halo here, or this large galaxy, wasn't properly centered in the data. So this might actually impact the results I show you today. But this object is at a very low redshift. It's quite a massive galaxy cluster, and it has a cool core, okay, which means we can expect a relatively large magnetic field at the center. We've also got this horribly named RXCJ blah, blah, blah cluster. Okay, it's quite a lot lower in mass than A4038. It's at a bit higher of a redshift. It's not a cool core, so it's going to have a slightly lower magnetic field. And we have finally A133. So we have some information about its properties. It's quite standard for a galaxy cluster. It's quite similar mass to the previous one, A4038. It is a cool core with this 8 microgauss projected central field, but it does have some nasty stuff getting in the way of our observations. You can see here some AGN jets, which make our lives slightly difficult. So these aren't perfect targets. We're still in the process of digging through all of the cases that don't have diffuse emission, trying to find the ideal target. So our method is quite simple, though it took a while to get going. We subtract the point sources. We only do this in the image plane. So radio astronomers will tell you should do this in the visibility plane because of non-local effects from the Fourier transform and things like that. But this is what we're doing for now. We will upgrade this in future. And what we do is we produce a map like the one on the left here. So this is a map telling you we're not really seeing any diffuse emission. These little islands are potential diffuse, are essentially what's left over once you've pulled out all the point sources. And this region here at the center is the central region we're interested in, because here is where the dark matter's density will be highest. So we can see there's not much diffuse emission in that area, which is very nice for our purposes. So what we'll do is inject dark matter emission. So what it would look like if there was dark matter emission. That's what we have in the second image. You can see we've suddenly got a bright point in the center. And what we do is we simply perform a chi-squared test between these two maps. And we find a 95% confidence interval exclusion for the annihilation cross-section for each dark matter mass. Now we consider both the conventional NFW halo, which is meant to be a good fit for galaxy clusters. So we're quite reasonably confident in the use of this profile. We also do a shallow cusp, just in case. It's a sort of worst case scenario. So what do our results look like? Well, for WIMPs, what you can see here is, again, limits on the annihilation cross-section. I've plotted in solid lines the Fermi gamma ray limits, okay? And these are 3 different annihilation channels. One where we go from dark matter to B quarks, one to muons, and one to tau leptons, okay? So this covers quite a broad range of potential dark matter annihilation models. So this, of course, will be part of a paper that's currently in preparation with my MSc student, Natasha Lavis, my PhD student, Michael Sarkis. So here what you can see is that we actually managed to do quite a lot better than Fermi-Lat, notably in the leptonic channels, the mu and the tau, but we also managed to exceed it at quite a lot of masses, especially the larger ones, for the B quarks as well. So the uncertainty bars here are just the difference between the NFW profile at the bottom of the bar and the shallow cusp at the top of the bar. So within the uncertainties, we do quite a lot better than Fermi-Lat. For A4038, this is the one that might be impacted by position calibration, as I mentioned earlier. These are extremely good results, but we can expect these to get a bit worse, unfortunately. As you can see here, these were actually better than the Large Magellanic Cloud, the Regis 2021. But hopefully we'll find a replacement cluster where our results are as good. Finally, we have the RxCJ cluster. These have much wider uncertainty bands. It seems to be much more sensitive to the choice of halo profile in this case. But as I said, we can be quite confident in the use of an NFW profile in a galaxy cluster, so we're not too worried about that. In the NFW case, we can see our results are excellent. They're competitive with the results from Regis 2021, and they probably shouldn't change too much with the change of with any kind of position calibration issues that we iron out in the future. So in terms of Axions, I'll show you some projections we've done for, because as the observations I mentioned earlier had been done using neutron stars in order to look for magnetic conversion. These projections here I'm giving are for the stimulated decay of axions in cosmic structures. And the reason that's interesting is we can cover a much larger range of masses than is possible with the magnetic conversion in a neutron star environment. So even though we can't do too well in our constraints, these are quite a lot worse than the existing MeerKAT ones, which are somewhere down near 10 to the minus 11. But this might be a fault in our analysis, and we might need to be a bit more sophisticated about the work we did here. And this is done by my former PhD student Ahmed Ayad and myself in 2021. So SKA, though, for the axions is a much more rosy picture for the stimulated emission case. It's very strong in radio galaxies. So you can see this limit here is the CAST limit set by the CERN Axion telescope, and we can exceed this quite substantially for these relatively low mass axions using galaxies like M87, radio galaxies like M87 or NGC 5128, both of which should be observable to MeerKAT, I believe. In particular, honing in on the core of MGC 5128, we get very, very nice limits here indeed. And the reason radio galaxies are so good for this is because they have the biggest baryonic backgrounds at the frequencies we're interested in. And as I said, this is the one time where we actually want big baryonic backgrounds when hunting for dark matter, because they enhance the rate of decay of the axion. Conclusions and for future work, for WIMPs, we can see we get extremely powerful limits from the MGCLS. They're competitive with the best ones in the literature, though the ones I present here are a little bit preliminary and may need some revision as we iron out kinks in the analysis process. So hopefully we'll improve this, though, with more advanced analysis, because we'll do things like subtracting the sources out of the visibilities and maybe getting a little clever with our statistics. So we're currently in the process of beginning a dwarf galaxy analysis with time. We got MeerKAT open time we received in collaboration with Prof. Njema from UKZN. We also want to look into the discovery potential. So if we saw some diffuse emission, how could we know if it is actually dark matter and not just some other baryonic process? So the discovery potential is an interesting question to ask. For the axions, the MeerKAT projections currently look weak, at least for this stimulated decay case. They might need more advanced simulations and processing, but we'll still attempt this on any dwarf galaxy and cluster data we can get our hands on. So the sort of take-home message from this is that we can do real cutting-edge fundamental science in South Africa, and MeerKAT and South Africa are on the cutting edge of these dark matter searches. Thank you.
Thank you so much, Dr. Jeffrey, for your wonderful talk. So if people who are in the audience, if they have any questions, they can unmute and ask the question. Yeah, Ahmed has a question.
Hi, Jeff. Hi, everyone.
Hey.
So, Jeff, I just have a general question about distinguish between a signal reduced from axions and WIMPs when we consider receiving the radio emission by MeerKAT or SKA. So instead of the mass will affect the frequency. Anything else can be a difference between the signals?
Well, so the axion, at least in the decay case, is a line, and the WIMP case is always a continuum. because essentially a range of electron energies are produced in the WIMP decay. So you get a range of different synchrotron frequencies, whereas the axion, it's always anchored by the mass. In the case, as I said, of magnetic conversion, it's a little bit more complicated. It's complicated a little bit by the magnetic field, but the behavior of the WIMP and the axion are quite distinct because, as I said, the axion has this peculiar interaction with the photon. That means the signal will look quite different.
Thanks.
There's a question from Edwin.
Yeah.
Yes, hello. What you will think about the difference about doing this, for example, with MeerKAT that works the data you are using is from the L band, and doing this with maybe in the UHF band, or for example with another instrument.
Yeah, so the frequency does matter.
It's a lower frequencies like GMR, so you have okay, yes, that was one question. And
Sure.
the thing is, how much will improve the results if you do the structure of the sources in the visibility plane?
Okay, so I'll answer the second question first. We don't actually know how much it will improve the results. It's a very difficult thing to estimate before you've done it, unfortunately, as most things are in radio astronomy. But it should be significant at least, because essentially when you source subtract just from the image plane, you are leaving behind flux that is that's been spread out into other pixels by the non-local nature of the Fourier transform. So the diffuse emission we see currently in the images will go down. So that's definitely true. So it should improve. For the first question, so GMRT is an interesting thing to use and has been used in some of those previous studies I showed. The results weren't great because GMRT isn't quite sensitive enough for this kind of work. And the big issue is GMRT also, you struggle with getting a really good source subtraction going because your resolution isn't fine enough. But I have actually been working with a Chinese group on FAST, doing this with FAST, and FAST is a little bit better at those kind of things. So we have been looking with a single dish in that case. So the frequency is quite important. The dark matter emissions are much larger at low frequencies. However, the issue is kind of the backgrounds. The baryonic backgrounds also rise with frequency. So in some cases, you can get a benefit from looking in the UHF band, though there's quite a lot of radio interference in that case. We do have UHF data on the dwarf galaxy that I mentioned in the conclusion. So we will look at UHF in that case. And S-band could be interesting because the dark matter particles tend to be more energetic than the background electrons that are just generated in the baryonic processes. And so the baryonic spectra should cut off faster. So the S-band might be able to give us an interesting look there. That'll probably work for larger mass WIMPs though, that produce energetic enough electrons to make it worthwhile.
Okay, thanks.
Is there any other question? Okay, if not, I have a question. So for your studies, you will be more interested in having a sensitive instrument, or you want to resolve the core? Because I can see that NGC, some radio galaxy, the core, just looking at the core gives you more handle on detecting dark matter. So maybe the instrument, like, would you need more sensitivity or high resolution?
Ideally, you want both, which you can't always have. But so sensitivity is usually the one you'd opt for, because you can always at least get a point source catalog done with, say, with a very high resolution instrument, even if it's not quite as sensitive, because you expect the point sources will be a good deal brighter than the dark matter emission itself. So you can't make that trade-off. The nice thing about the interferometers, though, is that you can do it all on one instrument.
Yeah. Yeah, and I had another question, but we can go to Ahmed questions before that. You can ask a question.
Jeff, can we go back to the parameter space for the axion when you show the MeerKAT, the limit?
Sure.
No, no.
Oh, not this one. Oh, oh, sorry. Okay, quite far back. Ah, there we go.
Yeah, I want to ask which process, I mean, produced this limit on
yes.
MeerKAT? And
so this was with the magnetic conversion process, and it was looking at magnetic conversion in the atmosphere of a neutron star.
That's interesting. Even it is still far away from the, I mean, cavity experiment, I mean, the limits from Edimex experiment. But
Yes,
yeah,
unfortunately so, yeah.
Competitive to it.
It's essentially just because the neutron star, although it has a gigantic magnetic field, which makes it great at turning axions into photons and vice versa, it is very small. So that kind of hurts you, because the probability of changing from a photon to an axion, or the other way around, it depends both on how strong the field is and on how long you spend propagating through it. So for a very tiny field, neutron star order like tens of kilometers, so you don't have much distance.
Yeah, that's very interesting. Thanks.
Thanks very much. I have a last question from my side. So when we're talking about removing the point source using the pi BDSF and then injecting a signal, so that injected signal is a simulated signal, or like how do you inject it? Like do you
you're literally just adding the maps together.
Okay.
You can do this injection in a more sophisticated manner, but so far we haven't done that yet.
Yeah, like even like you said, removing this point source in the image plane kind of has some residual flux.
Yeah,
remaining in your image. Yeah, like if you can remove, I mean, if you know the point source, its spectral structure exactly, like we can subtract it in the visibility space, and then even you can add your signal in the visibility space. That'll make more sense.
Yeah,
because
it would be a great way to do it. Also, though, the one thing that we're a little bit cautious about is that going into the SKA era, the visibility is going to be so big that it might not be very viable to do the subtraction in that case. So it's also worth looking into these techniques now.
Yeah,